Okay, so the next 4 days are going to be spent dealing with trig. Okay, today we're going to talk about trig integration. Tomorrow we're going to talk about trig substitution. All right, we will come back. For some reason, do you have your gold sheet? Anyone have their gold sheet handy?
Yes, I do.
Is the quiz Tuesday or Wednesday? I might have put that.
26.
Oh yeah. We spend 2 days on 8-4, then we have a review day, then the quiz is on Wednesday. Okay. So the next few days we're dealing with trig. Okay. You guys even know what this is referencing? Okay, that song is still like in your wealth of knowledge.
I've heard that line a lot.
Getting Jiggy With It came out when I was in like middle school, so it's been a while. It's a good old Will Smith.
I thought it was like tricky as in tricky. Like tricky integration, tricky integration. Yes.
No.
No.
Just triggy like trig integrals is what I was going for. Okay, you need to write these down. You should know the first one. But the second two are power reducing formulas. Okay. Power reducing formulas can be very, very helpful when dealing with integrals that have sine and cosine. Okay. You will use these two power reducing formulas often in the next 5 days, so memorizing them would be to your benefit. I want you to notice how here the angle is x, but here the angle is 2x. Okay. It doubles, right? So if the angle is 3x here, what would it be here? 6x. If it is 10 theta here, it would be 20 theta there. Okay? That's the relationship you need to remember. Okay? All right. So first, we are going to deal with integrals that have sine and cosine. Okay? Integrals that have a sine and a cosine in it, we know that u substitution could sometimes be an option because sine and cosine have the relationship of being each other's derivatives with a negative sign in there sometimes, right? So I would not write this whole thing down, okay? This thing that I'm going to show you is in your book. But what's important to understand is that when we have an integral where powers of sine and powers of cosine are multiplied, whoever is the odd one, okay, we're going to convert the rest. We're going to save one and convert the rest, okay? So if sine is odd, we're going to save 1 for u substitution and convert the rest to 1 minus cosine squared. Okay? Other way around, if cosine is odd, we're going to save 1 for u to u substitution and convert the rest to sine. Okay? If you do not if you have a power of sine or cosine without the other function, then we can use our power reducing formulas to help us there. Okay? Basically, whoever's the odd man out, you're going to save 1, change the rest. Okay? That is going to be our strategy. Okay? This is like copy pasted from the book. So if you need to reference it, you can. What I would write down is change the odd man. Okay.
Wait, for changing the odd one out, shouldn't we? Oh, never mind.
You leave 1 and you have an even number to change. which works out because we have the sine squared plus cosine squared equals 1 infinity. Okay, so we have to have an even number to do that. All right, so we're going to do a couple examples. Who is odd? Sine. So whoever is odd, we're going to break it up into a power of 1 times an even power. So in this case, sine times sine squared. Okay, so we have the power of 1 times whatever else. Okay, we're going to leave sine of x to the first power alone and change the rest. So sine of x is 1 minus cosine squared.
Wait. So we leave the odd.
We leave the odd, change the rest. Because the odd man is what we're going to use for our du in our u/du substitution.
What if you have two odds?
Then it would not matter which one you change. Okay? That's where it gets tricky. That's when you're going to have to use some of your power reducing formulas. We'll get there. Will we get there? I don't know. We'll talk about it later. Okay? So right now, I'm going to go ahead and distribute this out. We have sine of x cosine to the 4th x minus sine of x cosine to the 6th x. Are you saying what? You don't know how I got that?
Yeah.
Okay. We can distribute the sine through, and we can distribute the cosine to the 4th through. You with me now? Bailey? Cosine to the 4th times cosine squared is cosine to the 6th, and then that sine has to come through too. Cosine to the 4th times 1, and then sine times that. Okay, so now this works out very nicely for u substitution. U equals cosine x, so du is negative sine x dx. Okay? What I'm going to go ahead and do, this is going to make more sense.
Split it up.
Yeah. Like that. It's going to make more sense with two integrals. So both integrals have sine dx. Okay? So that gets replaced with negative du. And so what we have is negative u to the 4th du minus negative u to the 6th du.
What happened to the 1/2?
There is no 1/2.
Then we have to do sine squared x equals 1 minus cosine of 2x over 2.
It is, but we're using 1 minus cosine squared. We're using the Pythagorean identity here. We're not using power reducing. So then we have negative 1/5 cosine to the 5th x plus 1/7 cosine to the 7th x plus. I did my antiderivative and changed them back to cosine at the same time. Is that okay?
Yes.
Questions? Trying to do it quick. You just put it in.
Yep. Do my best.
Thomas, you have a question?
Yep. 20 single me out.
It's easier to look in your face like,
No. Same face.
just your face. Okay.
You can call me just face.
Okay. Now who's the odd man out?
First thing,
Okay. Cosine has the odd power. Okay. And like we said earlier, if they're both odd, you can choose whichever one to change. Okay, it wouldn't matter. So all right, sine to the fourth x times cosine to the fourth x times cosine. Okay, we want whoever's odd, we rewrite it so we have the power of 1 times whatever's left over. Okay. So now we're going to change cosine to the fourth. Okay. Cosine to the fourth is the same thing as cosine squared squared. Okay. This is why we want an even power, so we can write it in terms of either cosine squared or sine squared. So what we have is sine to the fourth x times 1 minus cosine squared, 1 minus sine squared squared.
wait, 4x.
Huh?
Oh, okay, sorry.
My 4 got a little big, sorry. Okay, so now what do we need to do?
Distributed.
Assumption to FOIL.
Yes. And we can do it now. Yeah, we can do it now.
So distributing is for
Boy.
All right. So we're going to distribute sine to the fourth times cosine to that trinomial. Ready? Sine to the fourth x times cosine x times 1 minus sine to the fourth times cosine times negative 2 sine squared. And then sine to the fourth times cosine times sine to the fourth. Verify multiplication. Huh? I was waiting so I could just break it up into 3. So we're going to do the same UDU substitution for all 3 integrals, but we're just going to write it once because we don't need to be redundant. What's U going to be? Which makes du cosine x dx, And we have cosine x dx in each of these integrals to replace with du, so that works out perfectly. So what we have is the integral of u to the fourth du minus 2 integral of u to the sixth du plus the integral of u to the eighth du. Isn't that nice to go to something so complicated and now we have just a simple power rule? Okay, I'm going to take the antiderivative and change them back to signs at the same time. Is that okay?
Yes.
So 1/5 sine to the fifth x minus 2/7 sine to the seventh x plus 1/9 sine to the ninth x plus c.
Do you have to separate or do you have to make the one integral into three, or can you just keep it all as one?
You can keep it all as one.
You can
integral.
keep
It's
it all
just
as one.
easier to do it.
And what you can do is, before your u substitution, if you keep it all as one, you can factor out that cosine of x. And then, I mean, you kind of see the pattern. So if you want to keep it all as one, it's fine. All right. So now let's talk about if we have an even power. What I'm going to show you first is just a loner sine or cosine raised to the even power. And then we can kind of talk about what happens if we have both sine and cosine with even power. But what we're going to do is cosine to the fourth x dx. I will tell you this is going to take up some room. So if you only have like this much left on your piece of paper, so you probably won't switch over. Okay? So it'll probably take up like half a page. Maybe a third of a page. Maybe a third of a page.
For the last one, I almost took it out.
You write really big though.
Did you write right?
It's in the number of.
You skip a line?
No.
I skipped a line on this one, one measure, but I asked you written on everything on the one end.
That's only one example?
Yeah, that was the last one. I literally wrote what was on the board.
I took over the line.
You went from like side to side like this. Like I was able to fit all that into one.
Okay.
I was
I'm
on
pulling my.
So
maybe if I was leaving.
if we have an even power and we don't have an odd man out to help us with u substitution, we have to use our power reducing formula.
Wait, we're throwing limits of integration in at the same time as the same thing.
So what we're going to do is we're not going to worry about limits of integration until the very end. Okay? It's going to take us some work to even get to the point where we can take the antiderivative.
Is there a reason that they both should have at the same time, or was it just like it doesn't have to be
Yeah.
to solve an even one, it doesn't have to be definite, right?
This is the strategy we'll use whether there's limits or not. Okay, so if we have a cosine or sine raised to an even power, we're going to use our power reducing formula. Okay? So cosine to the fourth x is the same thing as cosine squared squared. Right? And how can we rewrite cosine squared using the power reducing formula?
Plus cosine 2x over 2.
How I'm going to write it is 1/2 plus 1/2 cosine of 2x. Is that okay?
Okay.
If you want to write it as a big fraction, you can, or if you want to write it like this, sometimes it's easier to work with. All right, so now what are we going to do with that?
So something you would tell us.
Oh, do you have any suggestions?
Why is that 1/2 instead of 1 plus?
So you just split the fraction.
I just split it into two terms instead of one big fraction. So we're going to have to multiply this out. Okay, so this becomes 1/4 plus 1/2 cosine of 2x plus 1/4 cosine squared of 2x. Well, shoot. Do we know how to take the antiderivative of cosine squared? No. Anytime you have a cosine or sine by itself to an even power, you have to use the power reducing formula.
Wait a second,
So-
shouldn't the 1/2 cosine x be 1/4 cosine 2x?
Nope, because we have 1/4 cosine of 2x twice. So when we add them together, it'd be 1/2.
Oh, okay, I see.
Okay. So we're going to have to do the power reducing formula again for cosine squared of 2x. Okay? If there is not, in this case, a sine multiplied to any of our terms, we have to have cosine to the first power, otherwise we can't take the antiderivative. So we're going to do this one more time. Okay, cosine squared of 2x becomes 1/2 plus 1/2 cosine of 4x. Okay, so we used the power reducing formula on cosine to the fourth. We multiplied it out, but we still had a cosine squared, so we used the power reducing formula again. Now, we have everything as either a constant or cosine to the first power. Okay, we can take antiderivatives from here. Now, let's go ahead. We're going to need to multiply that 1/4 through and combine like terms. Okay, I think we're smart enough to do 2 steps at once. What is 1/4 times 1/2?
1/8.
And then we're going to have to combine that with 1/4. So we have 3/8 plus 1/2 cosine of 2x plus 1/8 cosine of 4x. All right, can we take our antiderivatives? Okay, all right, so we have, this is exciting, right? 3/8 x plus antiderivative here.
I think she's done.
So I think it's positive 1/4 sine of 2x. Yeah, I know, we gotta keep those straight. Okay, chain rule though, reverse chain rule, we have that 1/4, right, instead of 1/2. Plus antiderivative here. Evaluated from 0 to pi over 2. Okay. So 3/8 times pi over 2 would be 3 pi over 16 plus 1/4 times sine of pi
Which is 0.
plus 1/32 times sine of 2 pi minus 3/8 times 0 plus 1/4 times the sine of 0 plus 1/32 times the sine of 0.
So all that in our sign is going to go down again.
Would it be better if I erase those limits of integration and I just wanted the integer
No.
That was shorter than my list.
4 lines for me.
Only 4 lines? Nice, nice.
Shorter
The next
than
different
lines.
That took up like 3 lines.
Well, okay.
Look at
So, sorry.
Underachievers. Well, I got used to myself.
Okay.
Would you like a medal?
Another type of problem. Okay, so let's talk about if we have like sine squared, cosine squared. Okay. Notice how both power reducing formulas are in terms of cosine. Okay.
True.
So cosine squared times sine squared, I guess wasn't the best example. Well, regardless, both power reducing formulas are in terms of cosine, and so if both of them are even powers, then you can do the power reducing formula similar to what we did for cosine to the 4th, and then keep going with the power reducing formula like we did until you have everything in terms of just cosine to the 1st power. Okay. But I can't remember if you have a problem like that in your homework or not. You'll see a lot of these types, a couple of these. When we get into like tomorrow's stuff, we'll be doing a lot of like cosine squared that we'll have to do the power reducing formula for.
Do the power reducing formulas only work because it's in the integral, or would that also be equivalent if it was just like regular?
Anytime it works. Okay. We use it in our integral because we don't have an antiderivative for cosine squared, unless it's being multiplied to a sine. You know what I mean? Okay. So another type of problem you're going to see is when we have a secant and tangent, 2 powers together. Okay. Now secant and tangent have antiderivatives. They aren't each other exactly, but they're related, right? The derivative of tangent is secant squared. The derivative of secant is secant tangent, okay? So since that's the case, like if we have an even secant, then we can take secant squared out for our u du substitution and change the rest using the Pythagorean identity, okay? If we have an odd power of tangent, we can take a secant tangent and write it at the end and then use the rest for u du substitution. Let's remind ourselves of that Pythagorean identity. If sine squared plus cosine squared equals 1, what's the Pythagorean identity in terms of tangent and secant?
I think tangent 1 plus secant.
Okay. Imagine dividing all of those terms by cosine. Sine divided by cosine squared, sine squared divided by cosine squared is tangent squared. Plus cosine squared divided by cosine squared is 1. Plus 1 divided by cosine squared is secant squared. Okay, that is something that we're going to have to use to do these integratives. No limits of integration this time, so. Okay, so in this case, secant is even and tangent is odd, so we could go about this 2 different ways. Does anybody have a preference?
Secant.
You want to go through both ways to see how they're different? Okay. We have time. So the first way would be to separate secant by leaving out a secant squared. So we took out a secant squared. We're gonna leave this one for you to use substitution, and we're gonna change this one. What do we change it to? Look at your identity.
Oh no.
Oh no, what? Huh?
I was looking at
So if we take secant squared 3x times tangent cubed 3x and then distribute that into tangent cubed plus 1, we get tangent to the 5th 3x times secant squared 3x plus secant squared tangent cubed. Do you have an issue?
Oh. I see what you did, okay.
Okay. So then we can let u equal tangent of 3x, which means du is, careful, well, there's a 3 here, which means we'll have to put a 1/3 outside of our integrals, right? So secant squared 3x dx is present in our integrals. So what we have is 1/3 integral of u to the 5th du plus 1/3 integral of u cubed du. So our antiderivative is 1/15 tangent, nope. There you go. 1/18 tangent to the 6th 3x plus 1/12 tangent to the 4th 3x plus c. What did we start off with? Secant to the 4th, right?
Secant to the 4th 3x times tangent to the 3rd 3x.
Okay, so now we're going to do it the other way. Right. So the other way, since we have an odd tangent, we can take out each a secant and a tangent. Okay? So we can write secant x, tangent x, and then left over, 3x, I'm sorry. And then left over we would have secant cubed of 3x, tangent squared of 3x. What are we going to change?
I need to